This video is about how to measure the atmospheric water vapor with the global navigation satellite systems. But you may ask, why is water vapor important for us? Well, firstly, it helps us to predict the weather, because it's the main source of water in the rain clouds. And secondly, it's the most abundant greenhouse gas, accounting for 70% of atmospheric warming effect. Let's take a minute to have a look at the Earth's atmosphere. Imagine this is our planet, the Earth. As you may know, the Earth's radius is about 6,400 kilometers. The Earth's atmosphere is a thin shell of air which goes up to 1,000 kilometers. Let's now have a close look at its vertical structure. Do you know that some 90% of all mass in the atmosphere is found in the bottom 15 kilometers? The lower 30 kilometers contain 99% of the mass of the atmosphere. And above 1,000 kilometers, we could not distinguish it from the interplanetary medium. But we are interested in the bottom 15 kilometers, where the atmospheric water vapor is found. This layer is known as the troposphere. Tropos is a Greek word meaning turning and mixing. And indeed, the vertical mixing in the troposphere is such that if we take a drop of seawater, it can eventually evaporate and become a flock of water vapor molecules which can rise and condense and form a cloud, and then water can fall back to the surface like rain. And all this will happen within a week to 10 days. Indeed, 85% of water in the atmosphere is evaporated from the oceans, with the remaining 15% evaporated from the land. Interestingly, over 90% of water vapor is found in the lower 5 kilometers of the troposphere. How do we know, you may ask? Well, easy again, we can measure it. By putting a sensor on a balloon and let it fly off, we can measure the amount of water vapor on its way up. Easy, isn't it? This method is known as radio sounding. For many years this was the only way to measure water vapor in the troposphere. But this was changed with the development of the Global Navigation Satellite Systems, or GNSS. One of them is the Global Positioning System, or shortly GPS. The widely known application of GPS is position determination, with extremely high accuracy, better than 1 centimeter. Since early 90s, scientists have come up with yet another use of GPS, namely, to measure the atmospheric content between the satellite and the Earth. Now, do you know how GNSS works? Well, let's take a minute to explain it. A system of man-made satellites very far from us send a signal that travels with the speed of light and reaches the Earth's surface in about 10 milliseconds. 10 milliseconds are actually 1/100th of a second. But on its way, it passes the dense layers of the atmosphere and the speed is reduced a little. First is the dry atmosphere, a mixture of 78% of nitrogen and 21% of oxygen, which slows down the GPS signal, causing the time delay of 1 to 2 nanoseconds. When converted in meters, we can predict with high accuracy that it will add about 2 meters to the satellite receiver distance, which varies with up to 1% in a few hours. However, the actual measured distance is different. Where does this difference come from? The atmosphere consists of not only dry air, but also of water vapor. And importantly, water vapor has a very high temporal variability, changing from day to day, from morning to afternoon, from hour to hour, adding between 1 to 80 centimeters to the satellite receiver distance. So this is how you can measure water vapor using the Global Navigation Satellite Systems.